we did a little bit about atomic theory. Today, we basically covered the history of the development of atomic theory, and we got to the point of Rutherford's planetary model and why it was supported initially, but then it lost a lot of support because there was a bit of a problem with it. And so, we'll start with the journey with J.J. Thomson's plum pudding model, where before that they knew that atoms existed, or so there was a good consensus among scientists back in the day that atoms existed like as solid balls that were jam-packed together. Gases meant that the balls were bouncing around like crazy. In liquid, they flowed on top of each other. They were smooth. And in solid state, they were jam-packed together, like really, really close-knit friends. The plum pudding model proposed that the atom consisted of positively charged particles and negatively charged particles embedded in a lump of clay, basically. Apparently a popular dessert at the time, and referenced it as plum pudding. The reason why they went that extra step to say that there was positive and negatively charged particles inside the atom was because they knew of electrons. They knew of electricity at this stage, and they knew that electrons were a subatomic particle that flowed in current. And so they had to come up with an explanation of atoms using that concept already known. A couple of years later, so this was in 1911, Rutherford proved this. But it wasn't just himself. He had two other students, Geiger and... damn it, I forget the other name. I feel so bad. They performed this experiment where they got a thin sheet of gold. Okay? So thin, we're going to pretend that it is one atom thick. In reality, it was a lot of atoms thick. It was gold leaf. But we're with us. And they bombarded with alpha particles. Now, all they really knew about alpha particles at the time, because radioactivity was still not very well known, and they didn't know exactly what an alpha particle was. They just knew that it could be emitted by certain particles. And they knew how to detect it, of course. They knew that it was positively charged. That was important. They knew that an alpha particle was a tiny particle that was positively charged. Obviously, now we know it's a helium nucleus. And they bombarded this gold sheet with alpha particles. And what they expected was that as the alpha particles go through the plum pudding, right? Most of them would go through, okay? But if an alpha particle came really close to an electron or a proton, or a positively charged particle, it would slightly bend because of the electrostatic force. In reality, what happened was a whole bunch of alpha particles got the repulsed completely backwards. And they were like, what the hell? About 3% of the particles, again, I'm not sure if that's the right percentage. Roughly in my head, I'm trying to remember the results. About 3% of the alpha particles got yeeted back. And they were like, what? How did that happen? Well, they proposed this model, that the nucleus, the center of the atom, is actually positively charged while the electrons are orbiting around. And when an alpha particle is directed at the positively charged nucleus, it gets repelled back because of EM. They're two positively charged particles and they're repulsed by each other, and so it gets yeeted back. Taking a deep breath here. So, in conclusion from his results of his experiment, he concluded that the nucleus of the atom is positively charged while the electrons are orbiting around. Furthermore, he came with a planetary model of how this works. And the idea behind it is that he kind of used why it's called a planetary model. He used existing Newtonian physics based on planetary motion to equate it very similar to the electromagnetic force. So, as we know, when something is in orbit, for example, let's say we have a satellite in orbit of Earth, the idea behind it is that gravity is constantly pulling that satellite, right? And eventually, gravity will win over and it'll get sucked in. However, if you kind of look at it from vector perspective, perpendicular at every moment in given time, what's really happening is you're moving so fast in this vector direction. Let me draw it. Let me kind of draw it because it's weird to describe it this way. So that's Earth, and there's a satellite moving. This is a satellite. Okay, so we have a point here. Basically, what is happening is you have your speed going this way. Your vector trajectory is actually in this point, while also a gravitational pull happening because of the Earth pulling you in. And so at any given moment, technically your trajectory is ever so slightly shooting out of orbit, but because of the pull of gravity at that time as well, pulling you in, you stay in this perfect circular orbit. Another explanation that's really good of explaining this is that you're traveling so fast, perfect speed in fact, you're traveling so fast that you're missing the ground. So if you were not traveling fast enough, eventually what would happen is gravity would overcome your velocity, and the net vector, when you do the sum of the vectors, it will actually end up pulling you in and you will spiral inwards. But in reality, if you travel fast enough, the winning vector will keep you in orbit. Does that make sense? I keep wording this and going on a bit of a rant, and I apologize. I'm trying to explain it in many, many ways to see if it caters for a lot of people. But if you understand it as you're traveling so fast that you miss the ground, that's fine as well. That's a good answer. That's a good explanation as well. But hopefully with a little bit of visualization of vectors, maybe it helps as well. Anyways, I got on a bit of a rant. So that is how the planetary motion orbits work. So using the standard model, we have a standard planetary motion model. The force that is being pulled in this case, is not gravitational force, it's the electromagnetic force. It's equal to mv squared over r. R is the orbit, the radius distance from the nucleus to the outside, where the electron is traveling. But we also know that the force is electromagnetic, and we know what the electromagnetic force between two charged particles is. We studied this in electromagnetism, and that is F is equal to K, Coulomb's constant, times the two charges over r squared. Miraculously and crazily, we can say F is equal to F. So we can equate these two parameters together, cancel off an r because there's a similar r between them, and rearrange the equation to find V on its own. We're looking for the speed of the electron at any given point. Doing a little bit of rearranging, we actually know the values of all of this. We know K is a Coulomb's constant. We know E is the charge of an electron. We square it, don't forget to square it. M is the mass of the electron, and R is the distance, the average distance of the orbiting electron around the nucleus of a hydrogen atom. You can trust me, or you can skip on here and trust me that you can calculate it yourself, or trust me that is 1.6 by 10 to the power of 6 meters per second. We can determine its kinetic energy using the equation, half mv squared. I did a little bit of an electron volt calculation, where you divided by 1.6 by 10 to the minus 19, the charge of an electron. This is just to make the units a little bit more accessible and understandable, because we deal with so many small numbers. It kind of flies over a lot of physicists' heads. So to make it a little bit easier, we use the unit electron volt. And so the answer for the kinetic energy is 7.5 electron volt. And it happened to be that they knew the ionization energy of a hydrogen atom, and it is 13.6 electron volts. Now the answer isn't perfect, but it's in the right order of magnitude. And that is why initially Rutherford had a lot of support for this planetary model. Over time, a lot of people found a problem with it. The problem is that the electron, because it's orbiting around the nucleus, it is emitting electromagnetic radiation. And as we know, the law of conservation of energy cannot be created or destroyed. If it is losing energy, it has to lose something in the process. If it's losing electromagnetic energy in the kinetic energy equation, half mv squared, it is losing its speed. If it is losing its speed, remember when I talked about earlier how you have to keep up your speed to keep in orbit, otherwise you're going to fall due to the gravitational pull in the planet model. The exact same thing is going to happen here, except instead of gravity, it's the electromagnetic pull due to the positive and the negative charges. And so if your speed slows down, you're going to start falling into the nucleus and the atom will collapse. This model could have worked because we know that some atoms do collapse. However, based on the calculations, it would have collapsed really quickly and life as we know it could not exist. So after a while, the planetary model was not accepted. Next class, hopefully, we will talk about the atomic spectron Bohr model, but we do need to start with spectra so that we guys can understand a little bit about why Bohr's results were so freaking cool. But yeah, that is an overview of the history of the development of the atomic theory, part 1.